Hello everyone, welcome to this session. In the previous session we looked at the digital PLL, the block diagram of the digital PLL, and later we went to the hybrid PLL to undo the quantization noise of the TDC in the proportional path. So, let us begin with that and see how we are going to implement it. So, this is hybrid PLL, okay, analog digital. Want to write it, you can write it like this, analog slash digital PLL. Okay. So, here we had PFT, the implementation of the PFT we have seen, and then you had this feedback path from here. The PFT output goes to a DAC which I called as proportional path DAC or PDAC. Okay. The output of the PDAC goes to the oscillator, and this I am been using a current controlled oscillator. For example, the output of PFT also goes to a TDC. Quite often this is a 1-bit TDC. The output of the TDC goes to a digital loop filter. You can have gain if you want, and then this is 1 minus Z inverse implementation. The output of the digital loop filter goes to a DAC which is IDAC, current DAC in the proportional path, and this is what you have. Then the output of the VCO feeds back through a frequency divider. Okay. So, here what we have seen earlier is the implementation of the phase frequency detector, the TDC using delay elements or using a single D flip flop, your current controlled oscillator also. So, this is your out. So, just think about it, how we are going to control the current control ring oscillator using our proportional DAC such that there is no quantization noise. Okay. So, the oscillator which you have, while discussing the oscillator here, the ring oscillator in our case, okay. Now, let us call this a VDD oscillator, and you have current flowing through the oscillator. It will have a certain frequency, whether you control I oscillator or you control VDD oscillator. If either of these two parameters, control parameters I oscillator or VDD oscillator is same, the frequency will remain same in both the cases, whether the control is VDD or current. The other will just follow. So, this particular I oscillator can be controlled using a current DAC, and that is what your effectively your IDAC is doing. Okay. So, you can have a current DAC. Let me just make it here with switches. So, in the previous session we looked at that, okay, I can have multiple current sources, right, and the output of these current sources that is actually fed to the oscillator. So, this is I oscillator, I will just bring it down. Okay. So, this current source is fed to the oscillator like this. You are controlling the current. This control of the IDAC, IDAC digital, this is your IDAC by the way, and the digital bits which are coming DI, they are going to control this. Now, with respect to up and down signals, what we the way we can control this current sources, that we have, consider that you have these switches here, okay. These 3 switches here, okay, and then all are biased with a certain bias voltage, okay, such that when the switch is closed, at that time the current in each branch is I bandwidth if the switch is closed. Then the switch is controlled by your up and down signals. So, during the off state, when your up and down signals both are low, right, at that particular time you have only one switch closed. So, this is like you can say that there is a fixed current which is flowing here, okay, when you are having your up and down signals low. So, let me just first write it here, that what we want to achieve here with respect to your up and down signals, the current is not actually 0 or large value. It is, so you have this PDAC. The output of the PDAC is like this. You have this up and down signals coming in. If I call the total current output, which I will write this as IP, the IP current has the following format. So, you are having up, down and IP, the current which comes out of this proportional DAC. When your up is high, okay, and your down is actually 0, this is one case, or when your up is 0 and down is 1, these are the two cases, and when this happens. Okay. So, in this case what will happen here is, when up is high, the total current which you are going to have is I bandwidth. When your down is high, the current is 0, and when you have having both as 0, at that time the current is I bandwidth. Okay. So, what you are going to have is, when both the signals are 0, at that time the fixed amount of current I bandwidth flows through proportional path. When your up signal is high, you are having the phase error which is positive and you would like to increase the frequency, the current increases. So, from here if I just write the delta I, you are having plus I bandwidth, and when your down signal is high, your delta I is minus I bandwidth from the steady state. Okay. So, this is the logic which we need to implement here. Okay. So, let me just say, when your up is high and down is 0, that time the total current should be 2I. So, I give up bar signal when up is high, up bar is low, at that time you have I bandwidth coming in, and when you are having your up is 0 and down is high, okay, at that time the current flowing through the this particular logic is actually 0 only. So, if you look at it, you will have when down is high, it is here. Okay. Now, in this case just look at it, that when up is high and down is also high, what happens in this format, and this when up is 0 and down is 0. So, the thing which we have so far confirmed is, when up is high and down is 0, up is high, down is 0, you get I bandwidth here and there is no current in this branch. Whereas, when up is 0, there is no current in this branch and there is no current also in this branch. So, total current is, what you are getting is plus I bandwidth, you are getting I bandwidth, and the other one which you are getting is 0. In case when up is 0 and down both are 0, right. So, if up is 0 and down is 0, then you will have I by bandwidth current flowing through this, and there is no current here, because up is 0, up bar is 1, this value is 0. So, I bandwidth flows when up is 0, down is 0. When up is 1 and down is 1, in that case up is 1 and down is 1, this switch is open, this switch is closed, you have I bandwidth from here and you have 0 current from here, from this branch. So, let me just write it this way, that you are having, if up is 1 and down is 1, then you have I bandwidth current flowing in this branch and 0 from here. Okay. So, in both these cases, whether up is 0 and down is 0, you have I bandwidth current. When up is 1 or down is 1, then also you have I bandwidth current. When up is 1 and down is 0, then you have 2 times I bandwidth current total, and when up is 0 and down is 1, then you have 0 current in the at the output. Now, the third switch which I have actually added here, this is for giving some amount of bias current if in case you need. Okay. In case you need an extra current to bias the oscillator, you can always have the same amount of current and this switch is always closed. So, this is an always closed switch. So, just to understand this more clearly, I will now draw these switches controlled like this. Okay, these are the switches, and then the third one is something which you can always have as a fixed, always fixed bias current which is flowing through the oscillator, and then you have the actual current sources. Okay, you can have different multiplication factor here. So, the size can be y, here the size can be x in both the cases, and they are controlled by your V bias P. This is up bar, this is down. So, the total current which you are looking at here is I P. Okay. And when it is on, it is biased at such a voltage that the current which flows is I bandwidth. Okay. So, now just look at it for the case when your up is 0 and up goes high, then you have like this, just a waveform here to tell you how this IP changes actually, and similarly I will show you for the other case. This is one, and then the other down signal is like this, for example, just an example here. Okay. This is up and down. So, I am looking at IP. So, when up is 0 and down is 0, that means you will have this transistor on. The current which flows, right now you remove this, just discard this extra current from the third branch. You only look at IP, this is the control which you are having. So, IP is equal to I bandwidth. This is IP and this value is I bandwidth. When your up goes high, which means a bar goes low. When a bar goes low and down still remains low, then you have extra current coming from this transistor. The total current will increase to 2 times I bandwidth. When up and down both become 1, at that time these two transistors will exchange their role and the current will still be I bandwidth. It will remain I bandwidth like this. Okay. When your down signal goes high first and up bar still remains low, both these transistors are turned off and the current actually becomes 0. And then when your down signal remains 1, up signal goes high, this transistor turns on and the current becomes I bandwidth and it remains I bandwidth. The role only changes. So, what you are seeing here is from the bias point you are seeing plus I bandwidth, and here you are seeing minus I bandwidth. Okay. And this phase error, whatever phase error you have from the PFT, this phase error is converted to your I bandwidth for that time, okay, and which is going to change your oscillator's frequency. So, we also define KCCO, the gain of the oscillator with respect to the current. The units are going to be, you can say, radians per second per ampere. Okay, it is the current gain. It is like d omega out divided by the current in the oscillator. That is the gain. Okay. Now, IDAC is controlled in this manner because there are many bits. PDAC has the pulse width modulated signal. This is the best way to control the oscillator's current without having any quantization noise in the proportional path. So, given this, now you see that the control through the proportional path is going to be your I bandwidth times the phase error. So, I will just draw the small signal model of the PFT now, which has this phase error plus and minus. The phase error you have, if you look at the average current which flows out of this proportional DAC, that is going to be I bandwidth by 2 pi, okay, with respect to the phase error. This is the same thing which you had in case of your PFT output with ICP times R. If you recall your voltage control, delta V control, let me just put it back here. Your delta V control because of the proportional path was, in this case it would have been ICP times R, okay, and this would have been 0, and this case would have been minus ICP times R. Whatever your charge pump current is, that was the proportional path gain. This is the voltage, right, and ICP times R times your KVCO gave you the change in the output frequency. Now, similarly, what we are going to have here is the gain is here I bandwidth, because that is the change by which it the output current changes. So, we have this phase error gain 1 over 2 pi, okay, and from here it changes, you have this I bandwidth. This goes to your VCO, but the VCO has the other factor also coming in from the integral path. So, here I will write this as KCCO over S. The output of the PFT, what you are looking at, so the phase error detector, right, that particular PFT output goes to your TDC. Okay. So, you have KTDC here, then you had this transfer function which is Ki by 1 minus C inverse, then you have IDAC, which where you will have the gain of the IDAC. So, I will write that as your K IDAC, and all these things actually add up at the VCO CCO's input. Okay, so this comes here and this comes here, and this is your output. Here you have divide by N. Okay, this is a phi reference and this is your phi out. So, in this particular case, what you see is well, the loop gain is equal to your 1 over 2 pi into I bandwidth times KCCO over, or we can write it outside, plus KTDC Ki by 1 minus Z inverse Ki DAC, okay, times KCCO over S 1 by N. This is the loop gain, and from our previous session discussion, the bandwidth of this PLL is actually your proportional path gain. We worked it out earlier. So, proportional path gain, or you can say bandwidth of the PLL, this is hybrid PLL, analog digital PLL, is a proportional path gain, which is 1 over 2 pi I bandwidth times KCCO divided by N. Okay. Now, you may realize why I used the term initially bandwidth, because that actually turns out to be defining the bandwidth of the PLL. So, this bandwidth of the PLL is as your omega. So, if you want to increase the bandwidth of this PLL, then you have to increase this current source, the PDAC gain, by changing the current in the proportional DAC. Okay. You can work this out, the whole loop gain and other things. What you will find is roughly exact calculation will also give you bandwidth, which is quite close. Okay. So, now given this hybrid PLL, analog and digital PLL, and the proportional digital path control, let us look at how we are going to control through this IDAC, because this IDAC normally has a problem of your resolution versus range trade off. So, what is typically done? So, let us just, if we just consider the IDAC path and the CCO. Okay. So, we will only look at IDAC and the current controlled oscillator. So, what we have here is a large number of bits coming from the digital accumulator going to a current DAC. This current DAC directly controlling the current in the oscillator, or you can say the frequency of the oscillator. So, here I will call this as I integral path, II, or better let us say I int. Okay. So, now converting from DI to your IDAC, the thing is that the total current which is required for the oscillator to oscillate at a given frequency in our case. So, we also see that there is a additional current which is flowing in is I bandwidth coming from the proportional path. So, total current, this is I int and this is I total or I oscillator. So, I oscillator is your I int plus I bandwidth. Okay. There will be a limitation on I bandwidth, because the bandwidth which you can have is limiting your I bandwidth. So, we all know that the bandwidth of the PLL here is I bandwidth times I CCO divided by 2 pi n. So, K CCO divided by 2 pi n, this should always be less than equal to omega ref by 10 here. Okay. So, this is going to limit your I bandwidth, and quite often it may not also always be possible to have this bandwidth as the optimized bandwidth. Your actual bandwidth may be even lesser than that. So, I bandwidth is limited. So, for the oscillator to oscillate at a given frequency, a major portion of this total current comes from I integral. Okay. Now, when the major current is coming from this I integral, I int path, the problem is that all this current is based on the DAC which we are using right now. So, just take an example. If I have 10 bit at the input, right, So, these 10 bits which you are having, you need to convert this using a 10 bit DAC. We saw this thing in the previous session, that I need to have the current sources like this. Okay, we looked this in the voltage DAC, now I am looking this in the form of a current DAC. Well, fine, a minimum of 10 unit elements are required, okay, 10 elements are required such that the current is I naught, 2 I naught, and similarly 2 power 9 times I naught, and then these switches are controlled by your DI. Okay. Now, the problem here is the following: in a steady state, your TDC which you have seen before, this particular TDC will keep on having, because if you want to use 1 bit TDC or any other in the locked state, you will keep on flipping the TDC output between 1 or 0. Okay. Let us say even the last bit will keep on flipping 1 or 0, which will keep on changing your current or your DI by a minimum of plus minus half LSB. So, you can keep on switching between, in the locked state, DI may switch between plus minus 1 LSB, or it can also have in the steady state whatever the value it has, it may switch between plus minus 1 LSB or between 0 and LSB, and that way your current is going to be switching between whatever 0 and I naught. So, you can say minus I naught by 2 to plus I naught by 2, and if the changes are a little more, then you will have maybe few LSBs, plus minus few LSBs. So, what happens is that in response to this minimum LSB size which you are having, this current actually changes. If I write from the integral path point of view, delta I oscillator will always be greater than every clock cycle. Your delta I oscillator is changing by I naught. So, you can say either 0 or I naught or minus I naught to plus I naught, that is the minimum, it is going to be greater than that, which implies that delta f of the oscillator frequency is going to be most of the time greater than your I naught times k CCO. This is the change in the output frequency. So, if you have an oscillator where your frequency is, it is changing randomly, but it is changing by every other cycle, it is changing by I naught times k CCO, this is going to create deterministic jitter, or you can say this will increase jitter at the output at PLL's output. Why it increases? Because steady state requires some fixed value of current, but the current, whatever that fixed value is, from that fixed value the current is always changing like this. So, I can write that in a steady state I oscillator is some fixed I plus minus n times I naught by 2, where your n is equal to either 1 or 2 or 4 or so on. Okay. So, this is going to create the change in the frequency, and if your frequency changes every other clock cycle, you will have the additional jitter at the output. The way to address this is that I go and keep on reducing my I naught. Okay. The way I have told you that, okay, I am having 10 bits, but actually the bits which are coming from your integral path are many more, because you are integrating it, whatever bits you have, right. If you are having 10 bits and you are implementing in this manner, that is the max which you can do. Now, if I say I am going to reduce my I naught, if I reduce I naught, then what happens is the total range of the frequency variation by IDAC reduces. What is the total range? Range of IDAC? Range of IDAC is nothing but you can say approximately 2 power n times I naught, in our case 2 power 10 times I naught. So, if I am going to reduce my I naught to reduce this jitter, then I am reducing the range of the frequency which can be controlled by IDAC. Okay. So, there is a range versus you can say resolution or range versus jitter trade off due to IDAC. This you will see. Okay. There is one other problem. The other problem is implementing the way I have shown you. This is like a binary DAC, where each current source is actually having 2 times 2 power n times the current value. Now, this DAC itself suffers from a lot of non-linearity. So, it is like this when you are switching from 63 unit elements to 64 unit elements, all the LSBs have to be turned off and only one MSB turns on. So, this is the point where you will mostly see errors, big errors. Then if you are just switching like from 13 to 14, if only one LSB switches, then the error is different. Though, so example is for the IDAC, switching from 63 back and forth to 64 will give you large errors in this kind of DAC implementation. Okay. Whereas, if you are switching from 4 to 5 or let us say you are switching from 4 to 5, where only one LSB switches, not all the current cells switch, that will give you a small error. So, error is actually it depends on though it is only one LSB switching, but it depends on which bits are being switched. And in order to make sure that there are no errors or the errors are limited, well, you have to have a lot of matching requirements. Okay, even then such problems will exist. So, what other thing is done to implement this DAC is to have better linearity, that all these elements they are having the same unit element. So, this if this is controlled by D0, then for D you can have binary input, but the control is more of a thermometer one. So, this is I naught, this is also I naught and this is also I naught, and these two are controlled by D1 bit. Similarly, you are going to have 4 current sources, okay, like this for D2 control, and all the current sources are like this. So, you have to spread it out, and if you implement in this particular manner, right, then the matching between the current sources is good. The errors while switching from one LSB to the other LSB, one value to the other value while changing only one LSB will be minimum. But as you go ahead and do this, the number of unit elements which you need to have will just increase in the order of 2 power n. So, you can see now for 2 power for 10 bits I need to have 1024 elements, which is a problem. Okay. So, looking at both of these things, what we do is the previous approach is good approach in terms of matching, in terms of minimizing the errors, okay, but it is quite cumbersome to implement and manage the matching between them. So, what is done is that your DI, which is coming from the, this is a digital signal which is coming from the integrator, is actually quantized using a digital delta sigma modulator, okay, So, do not worry much about it. I will tell you the basic operation. So, you can say d I delta sigma. This is implemented using the thermometer DAC as you see here. This is, by the way, you can call this as a thermometer DAC. Okay. This is implemented using a thermometer DAC here, and this will give you the current. If you want to convert into a voltage, you can convert it into a voltage. Now, what is happening while going from di to di delta sigma? So, what this particular, let us call this as DSM, that is better. Okay. So, going from di to DSM, what delta sigma does is, this is a digital delta sigma modulator, which takes this whole like a 10-bit number, and it may give you, depending on what you want, a 4-bit number or 5-bit number, lower bit number. Okay. So, specifically what we are saying is this, just think it in this way, the di range, whatever this digital bits you need to think, you are having 1, 0, 2, 3 here. These are the levels for digital. I am writing their decimal equivalent. So, there are 523 intervals here. You convert this whole unit to only, let us say, few intervals. If I am saying 4-bit, we are having only, I need to have more, but we need to have only 15 intervals. So, the range is maintained in both the cases, but here you have 1020, just easy number, 1024 levels. Here you have only 16 levels for a 4-bit. It is effectively saying I want to match the total current. So, for example, if this di bit while going through an ordinary DAC would have given me di digital control going through ordinary DAC would have given me a current range of 1023 times I naught. Okay. Even DSM going through an ordinary DAC should also give me 1023 times I naught. It should, this range is maintained, just that is the important part, but this here is a 10-bit number and this here is a 4-bit number. Okay. You can think about it, the easiest way to do is that I take this 10-bit number di. So, I am having this 10-bit number coming in, I drop 6 LSBs and I just take 4 MSBs. Okay. And I control the same IDAC. So, if you have only 4 MSBs, then you need only 4 binary weighted current sources or maybe 16 current sources which are with same unit element. So, this is one way of changing from 10-bit number to 4-bit number while maintaining the range. The other way is that you change using delta sigma. The difference between this method and delta sigma method is that when you are dropping the bits like this from the actual value, you are having a quantization error added to the signal, because the actual signal is this, but you are representing by only 4 MSP. So, whatever is the rest that appears to be, that is now a quantization error. Similarly, when you are converting from DI to DSM, you will also see the quantization, and the only difference is that this quantization error, when you are going to see at DSM output, this quantization error is noise shaped. Okay. So, we will not go into the detail of how this noise shaping happens. You can very well read about it. The idea is that you convert a large bit number to a smaller bit number using delta sigma, such that you shape the quantization noise while converting from the larger number of bits to a smaller number of bits. And this delta sigma modulator actually operates at a certain clock. Okay. Depending on what the clock frequency is, you will see the noise shaping, but for now you can say that this is a technique which is used to reduce the number of bits. Now, implementing a 4-bit thermometer DAC here is much easier than implementing a 10-bit thermometer DAC. Okay. Now, given this, that I can control the PLL in this manner, let us just put everything back and then talk about how we have actually solved the problems, or what are the problems remaining. So, here now what we have done is this PDAC is something we know now. So, let me just do this. Your up and down signals, they are going to come to an oscillator. So, and this is DI. So, this DI is going through a digital delta sigma modulator. Okay, this is clocked. The output of this digital delta sigma modulator will mostly have lower number of bits, TDSM. This goes through a thermometer DAC, like I will just give you some block representation of that. Okay. This thermometer DAC is like switches with currents. You can, by the way, you can also convert this to a voltage and use that. So, this DAC now controls your oscillator. Okay. Similarly, your up and down signals which are coming, you can control it in this manner, that you get up bar here and down here. Okay. And these two are controlled. You can have a fixed bias current if you require. This is a bias voltage VBP. These two are also going to give the current here. Okay. So, this block is your proportional DAC and the other block is your integral DAC. Okay. So, these two signals come here. So, what we have done so far is we have simplified, or you can say we know how to control our PLL, okay, using these current DACs. Okay. So, this is yes thermometer DAC. Now, the problem as you go on implementing and realizing a certain resolution, you will not feel that much of an issue with the proportional DAC, okay, but with IDAC implementation, the range versus resolution trade off will always be there. Okay. So, you come up with some other ways, you can give extra current as required, that will be for you to read about, right, and then you can actually create, you can have an extra DAC which feeds into this oscillator. That is perfectly fine. Now, when we are going to model this PLL, there is one thing which we have not added so far, that this node, though we are controlling only the oscillator current, right, this node actually comes with good amount of capacitor. It is not that this node is you have I and that it directly goes through the I goes to the oscillator. So, let us call this as CP. Okay. So, what happens is your loop gain transfer function now, let us say this is you are having whatever current gain you have that you are adding here. So, the change in the loop gain you will see, I am going to have 1 by 2 pi times our I bandwidth. I bandwidth is the current which will come, the gain of the proportional path with respect to up and down. You have I bandwidth here, and then plus you are having this KTDC times your 1 by there is a gain here also involved. Let us just write that, depending on how many bits you are dropping or what you are multiplying, Ki by 1 minus Z inverse, delta sigma and everything else will do. So, just only the signal path. So, from here to here, what we do is, what we have is the ST, the signal transfer function, or STF, remains same. Okay. So, this gain from the input of the delta sigma to the output of the delta sigma for the actual signal is the same. So, that gain is 1. Okay. And then you have K IDAC, whatever gain we would like to implement, that is what you have. All this current, it does not directly flows through the oscillator, it sees this capacitor also. Okay. So, the modeling requires that we take this I, whatever the current goes to the oscillator, and then we find out what is the output frequency. Okay. So, here we come up with this logic that in a steady state, okay, when you have all the currents are fixed, there is only the noise and the variations you have, I can model the VCO, okay, using its equivalent resistance, and this particular current goes through this R VCO times Cp, that is the pole. So, you can say this current goes through this oscillator and the capacitor, which is R VCO in parallel with your 1 over SCP, right, to give you the control voltage whatever you have VDD oscillator, and then from that voltage to output frequency we know it is K VCO over S, this 1 by N. Okay. So, to simplify it further, we have 1 over 2 pi I bandwidth, I will just put everything as K I dash times F ref by S under the approximation, right, and then you are going to have this R VCO parallel SCP, that is going to be R VCO divided by 1 plus S times R VCO times Cp, okay, into K VCO by Sn. Okay. So, now you see we started with the digital PLL, which was only second order. Because of this capacitor and the kind of control which we have, it becomes a third order, and you have a third order system, 3 poles, and the pole is mostly dominated by the Cp. So, now I will bring back that we added the ripple capacitor earlier, ripple bypass capacitor in our regular analog charge pump PLL. In this case, we did not add an extra bypass capacitor, but the parasitic capacitor which is existing at the VDD of the oscillator, it provides you the third pole, and it will help in reducing the ripple because of the this proportional path, or because of the whatever the residual delta I you are going to have from IDAC, it is going to have the ripple there, and it will help in having the ripple bypass. Now, whether we want to go ahead with whatever the ripple bypass capacitor gives us, or if we want to change this particular pole position, we can go ahead and add extra capacitor also. Okay. Now, you can this is the 3 pole 1 0 system, and you have to keep it stable. So, you can go with the same process which we used initially, that we want to have the maximally flat phase response at the unity gain frequency, would like to have the positions of poles and zeros. So, with that method you can find the location of Cp or the value of Cp, the gain Ki dash and other values. Okay. So, this is a very basic digital or you can say hybrid analog and digital PLL with all the given controls. Okay. One other thing which we need to know here is that when you are doing the quantization from DI to DSM, a lot depends on this frequency, clocking frequency. Okay. If this clock frequency is higher, then your noise will be filtered off more, the quantization noise will be filtered more. Okay. And just to tell you that differentiate between this conversion from directly dropping 6 bits and or doing through delta sigma, the difference is this, that the quantization noise in directly dropping 6 bits, that quantization noise spectral density will be flat. Okay. This is quantization noise while dropping bits with respect to omega. This is a noise spectral density, is going to be flat, whereas when you are doing the quantization using digital delta sigma, it is going to be something kind of this. It is called noise shaped. So, within a certain bandwidth, within a certain band that happens to the bandwidth of the PLL, the noise is much lesser. Okay. So, this is your quantization noise with digital delta sigma. Okay. So, and this kind of noise shaping actually depends on the clock frequency which you are using. So, quite often this also happens that you do not clock it at the reference frequency, you may take this clock and maybe divide by some factor n1 or some value and use this clock to shape this noise better or something like this. Okay. Those are the details which one can look into when one is designing the digital delta sigma modulator. If you are not using digital delta sigma, you can very well go ahead with this, but then you have this quantization noise, you have to have a lower bandwidth in the system. Okay. Thank you.